Hello, and welcome to this virtual session pre-recorded of Structure and Function in Physics. I'm Dan Voss. I teach physics and chemistry in Iowa.
Hi, everyone. My name is Sunny Santaranan, and I'm a high school physics teacher at Adlai East Stevenson High School in Illinois.
And today we're going to basically talk you through a unit that we developed, both its history and rationale. Then we'll start to talk through just the general arc of this unit before really hitting the structure function thing hard. As you saw in the title, we found an opportunity here to really work structure and function into physics versus it's very common in biology. We don't really mention it in physics. But we think it's important because it helps students understand the difference between analog and digital technologies and how this all relates to waves. And then we'll end with next steps and where to find out more. So we hope by the end of this, you buy our philosophy or idea that students really need to understand that difference in order to be able to think about digital tech, and that structure function relationship is important to their deeper understanding. And finally, that actually that structure function focus can really help bridge that connection between what's going on at the storage level and what's going on at the transition level and with the actual electromagnetic waves. So a little bit about the history of this unit. Actually started back in 2015. I put together with a collaborator just a short 3-lesson sequence on cameras and kind of identifying the difference between digital and analog technologies. I wouldn't say it even hit the performance expectation about digital technologies in depth. It was just kind of the hints. Then during the next couple years of teaching, I expanded that into a full unit that I'd say hit that performance expectation pretty well, before expanding it then to include waves. And basically now what we did in the last year during quarantine is we try to revamp this unit to really be more coherent, to do a better job of addressing transmission and the role of electromagnetic waves. And so this current unit has all the waves and technology performance expectations for high school. Also, we've kind of shifted, so we're no longer focusing quite as much on cameras as in this original unit. The anchoring phenomenon is videos now, but cameras obviously still play a big part of the unit, and that's what we'll focus on today. And we're hoping to start piloting this new version this spring. Now, what you're about to see and what we'll actually give you access to in terms of the storyline is not a finished product, but we wanted to put it out there so we can get some feedback from others. And really, this will help us process it, what's going on with it as well. So the reasoning for this particular unit is that the digital analog thing is really tricky for students. And notice I said both those terms together. The standards only talk about digital. I'm not even sure they mention the word analog by name, but you really can't understand what it means for something to be digital if you don't understand what came before. Students, though, normally when they hear digital, they just think that means computers, anything to do with computers, and they don't know what analog means. But really, in order to understand the advantages and disadvantages of digital tech, you actually need to understand how and why they work. You need to understand the waves component, and you need to understand what it actually means to be digital or analog. And so in this unit, we're really trying to help students make those connections in a way that's meaningful to them, which means that we're actually using technologies they're familiar with, or in the case of some of these technologies, ones that they might see sitting around on older siblings or families, shelves all dusty like records. But we find that students actually want to be able to explain these technologies. They kind of seem magic to us, right? When we talk about phones or computers, but really there's very particular structures that make these things work. And we really want to bring students into the joy of figuring that out in this unit. This unit was designed as a storyline. So if you're not familiar with storylines, I really encourage you to go to one of those 2 sites there at the bottom to learn more about them. But the idea behind storylines is that student questions are driving the investigation. And so you start with some anchoring phenomenon, some interesting thing in the world in our unit that is trying to send a video to a friend. And then students ask questions about that phenomenon, investigate those questions, and then finally they're able to build explanations or models based on those investigations that they conduct. So the idea is really to engage students in the process of doing science and make them be scientists as much as we can in the classroom. And so we'll have a few of these throughout the video. This would be a good moment if you just want to pause, jot down anything you've thought of so far. And in particular this time, do you know what analog and digital are? Take a second, think about that distinction, and try to jot down for yourself how that actually relates to waves.
All right, so like Dan mentioned, the anchoring phenomenon for this unit revolves around videos, how they're recorded, sent, and received. And with all the technology that we have access to these days, it's something we do take for granted. So our hope is to take students on this sort of journey to make some meaningful sense making. So in our kickoff lesson, students will record videos of one another, try sending it to different phones throughout the school. And from those initial observations, we'll generate these questions that will drive the rest of the unit. And we've broken down the storyline into 3 distinct bends. This first bend focuses in on sound, and we start here because students will have more familiarity with some of those concepts. We'll dive into sound production and recording, and we'll investigate specifically mechanical waves, their properties, and their behaviors. And then we'll sort of shift to the video aspect of it all, which is a bit more complex, a little unfamiliar to students perhaps. And we'll take a look there at old cameras, new cameras, and really take a look at how the structure of those parts, those pieces, are connected to its function. Essentially, how are videos captured and stored? And then finally, we bring all of that knowledge to the third bend, where we broaden our exploration of the different technologies. How do we use light? How do we use sound to encode and transmit that information? So in this last bend, we'll emphasize those wave properties, specifically of the electromagnetic wave spectrum, and we'll include some more informational tech concepts, such as binary coding. The standards that our unit covers comes from the next generation science standards. Like Dan mentioned earlier, we revised these curriculum to include all the performance expectations for waves and informational technology. So you can see how we've distributed standards throughout the 3 bends of the unit. Our initial lessons build up sort of these physics principles about wave properties and wave behavior. And later on, we shift our focus to constructing those explanations and claims for the advantages and disadvantages of different communication technologies. So next I will share an example lesson from our unit. Here is lesson 11, or just a snapshot of it rather. It's the final lesson in bend 1. So before this lesson, we explored all sorts of, sound phenomena, ranging from quiet rooms to bone records where music was actually encoded into bone. The cross-cutting concepts we emphasized in this bend were structure and function, just introducing that, some patterns, some cause and effect, especially in relation to wave behavior. To apply that knowledge of mechanical waves that we've been building up towards the technologies, we took a look at recording devices. So in our original anchoring phenomena, we had some ideas about how that sound was recorded. And so in this lesson, we take apart a phone or look at some photos. We noticed that there was a microphone there. It was attached to circuit boards. Perhaps there was a magnetic membrane there. We might not be so sure about how it works, and it didn't really help us figure out how sound was actually recorded. So to sort of help build that picture, we wanted to take a look at some older sound recording technologies. So from vinyl records, we zoomed in and observed that there were these continuous grooves on which the sound had to be encoded. We also looked at CDs, and what we noticed there were these little pits for which the sound was also encoded. And these observations introduced those ideas of continuous analog signals and discrete digital signals. And the interesting thing was when we test piloted this lesson, some of these kids never really saw, a CD or a vinyl before, which was it just kind of brings back that nostalgia piece. And so can you just imagine if we brought out like an 8-track or a cassette tape? It'd be a little bit trickier. So we were just focusing in on these vinyl records and CDs just so that we can zoom in and see what's actually going on with how that sound is recorded. So the big takeaways from Ben 1 are that students should be able to model the production and propagation of sound, as well as what happens to those mechanical waves when they meet certain physical boundaries. And from there, they'll be able to explain some real world phenomena. We would definitely look at the Doppler effect or breaking drinking glasses with voices. In addition, they'll start to make connections between some old technologies and new technologies and thinking of those advantages and disadvantages. And after this spin, students might start to wonder, okay, well, now we kind of have an idea about sound. What's going on with that video component? How does it get recorded? And what does light have anything to do with it? Before we go on to the next bend, let's just take a moment and pause to reflect on any questions you might have had in these past few minutes. How does our approach in bend 1 different from how you've maybe addressed these in your own classes? What questions do you think students will have at this point?
Okay, so where we left off in the first bend was students maybe starting to wonder a little bit about what is video, how's it recorded, how does light work? In the first couple lessons of bend 2, we answered those questions by actually figuring out that video is just a series of pictures, just a series of images like you would see in a flip book. And then light, we actually investigate and realize, and this may be a review for some students, but light moves in straight lines. And when it interacts with a surface, it's going to either transmit, reflect, or be absorbed. That leaves us in a place then that we can actually figure out how these images are captured. And so we could start with kind of one of our actual phones. We saw in lesson 11 that sometimes it's hard to figure out what's going on in there. So let's start with an old technology, kind of like we did in lesson 11 then. And so we're going to start with tearing apart film cameras. Now you can actually still get disposable cameras in bulk for a fairly reasonable price, but the prices are starting to go up. So in the future, I'm probably going to record myself dissecting one of these so it's available to students and posterity once these things become really difficult to get. Sometimes you can also get like a Walgreens or something to give you some old ones too that they process, but that's getting trickier as well. But anyway, we rip into these disposable cameras and students tend to be fairly surprised by what they find, particularly students in like kind of the earlier high school range. I've actually had students be pretty convinced before that there's a printer inside when we piloted just this part of the unit. That of course is not the case. It's, you see that circuit board in there and that looks pretty complicated, but really all it is you've got this film and the only other thing that the film is connected to is a dial that advances it between different parts of the film. Otherwise though, everything else in there seems almost a little bit superfluous. And so the way that we frame this lesson, as you think about this almost like a dissection in biology, we identify different structures and then we talk about what functions they might serve. And one way we decide to frame this is which parts of this camera are absolutely necessary to get a single picture. The most common responses we get are below. Some students absolutely insist that in addition to the film, lens, and shutter, we need the flash. Some students are also very insistent we need a button to tell it to take the picture. And those are all perfectly reasonable things to say. But then as we start to discuss it more, some of our classmates start to point out, we really don't need that flash because you can take a picture without the flash on. You can, cover up the flash and it still takes a picture. It's just not always necessarily a good picture. Also, that flash, as I said, is not really connected in any way to the film. So it must not be necessary. And And so often at this point, we're down to these last 4 items as being absolutely necessary. And then we read a little bit about pinhole cameras, the simplest camera possible, which is just a box with a tiny little pinhole in it and film in it. And you pull up or somehow open some sort of shutter to let light in. And then the film is exposed and creates a picture. And once students see this, they're like, you know what? We don't even need a button. All you really need is that film. You need some sort of lens or hole, and you need a shutter to keep the light out unless you want it out. Some classes also choose to add the body of the camera to that list as well. And from that, we can develop a model. A typical example is shown on the left there that shows the light coming in straight lines. And when the shutter is open, it comes through and exposes the film. And we know that some sort of chemical reaction happens on that film. You can go more in depth if you want, but I've always kind of just left it there, unless students seem really excited to learn more about the actual development process. So now we know how these older cameras work, and we've got some things we can maybe apply to newer cameras as well. We can apply to digital. And so obviously it's much harder to get digital cameras for dissection. And so we watch a video that does this, and we set up this organizer. The class kind of talks about this type of thing beforehand to identify the different parts of a film camera and what functions they carry out. And they often come up with a list that looks a lot like what I have here. And then we watch this digital camera dissection, trying to think of, do digital cameras have this part? And we end up with a list like this. You can argue some digital cameras don't have a shutter, but at the very least, they basically turn off to prevent light from entering when a picture is not being taken. And then really the only other structures that are missing from the digital camera are there's no viewfinder like in a film camera. There's no little window to look through. That's because instead there's actually a viewing screen. Most classes pretty quickly decide that that's not a relevant difference. That's not that important. But then of course, digital cameras don't have film, which any student can predict, but what replaces it? Well, first of all, film does two things. It captures the light and then it saves the image. And so in a digital camera, we replace that with light sensors to capture the light and then an SD card to save the image. And we look at those light sensors a bit and have a reading that talks about pixels and cameras. And you see that it forms this grid. Well, think back to CD versus records. The CD stored the information in little pits, and these pixels or these little light sensors in the grid remind us of those pits. So digital cameras, just like CDs, are storing that information in pieces, whereas film cameras, just like the records, are storing that information in a more continuous way. And so here we really see another example of this digital analog difference. And once we have that, we can really start to think about those differences between our older analog and our newer digital technologies. And most students think, well, digital technologies are better in pretty much every way. Some would argue in terms of security, it's not as good. But we start to realize after discussion that these differences come down to differences in the structure. So the function depends on the structure in all these cases. And so something about storing information in pieces actually helps us do a lot of different things with them. And our initial gut is that makes sense, because if the information's in pieces, then it's way easier to copy a bunch of pieces than it is to copy a whole new thing, if you're trying to say make a copy of a picture. But what's actually going on under the surface? Because we know this isn't magical. There's more to it than what we figured out so far. And how do all these different devices talk to each other? So this is where we actually dig into the code a little bit. And you can do a really cool thing on Macs where you actually just change the extension on a file from, say, a JPEG to a text. And from there, you can just delete big chunks of what's there or alter big chunks of the text that's there. Does have to be pretty big chunks to make a noticeable difference. But when you do enough of it, you start to see noticeable differences in the image once you convert it back and open up that JPEG. You know, I do one where it's a cute little puppy and you mess around with it. And then afterwards, the puppy tends to turn weird colors and there might be chunks of his face missing. So it's very memorable. Now, most students have heard of binary code or something like that. Even if most haven't, there's usually someone in the class that's pretty familiar with it. And so when I ask, like, you know, what is this language thing? They're like, well, it's code. And then we introduce binary code and kind of go through how binary code encodes text versus numbers versus images versus sound. And then we kind of apply that back and we think, okay, so like digital cameras, each one of those pixels is going to represent a color. And based on the light that comes in to the light sensor says, okay, you know, I've got green here, so this is going to be a green pixel. And then the memory card stores the section of binary code that means green. You can do the same thing with CDs. You can do the same thing with any digital tech. And so that's how, with ones and zeros, we can really convert between all these different types of information in just a really fascinating way. And so then too, a lot happens in terms of the structure and function piece of this. But really, students by the end of it should be able to explain how light works, talk about the differences between film and digital cameras and model that, and then also argue how binary code, how storing information in pieces really helps make digital technology special. But there's still pieces we haven't answered yet. For example, our initial anchoring phenomenon, we're trying to send this video through the air. So we're sending ones and zeros through the air. How's that work? I mean, a lot of students' initial models say, oh yeah, it's radio waves or it's cell phone waves or something, but they can't actually articulate what it is about those waves that's interesting or special. So with that, take another minute to pause, think about how this is different from the way you may have addressed these standards, think about other student questions, and then once you've had a chance to reflect, please move on.
All right, so as Dan mentioned, we left off in Bend 2, just wondering about how these signals actually get transmitted. Like, are there actually ones and zeros floating through the air? Well, we realize that these are things that are a little bit hard to see. And so Bend 3 is now kind of looking at the applications of these waves, how they're transmitted. And so we start this bend by taking a look at a very common piece of household furniture, if you will, the TV remote. So we'll explore different remotes along with some different appliances and just try to make sense of why certain buttons correlate to specific functions like volume up, volume down, and why can't I use this TV remote to turn on the microwave, that sort of thing. The signal that's transmitted from these remotes is not super visible to the human eye. So then students get to think about, you know, that broader spectrum of light, or what we'll call the electromagnetic spectrum. And the cool thing is, using a phone camera, though, we can detect some of these signals. So here in this little GIF, I think it's GIF. I'm not sure if it's GIF or GIF, to be honest, is we have a controller that I kind of aimed right at the camera. And once I pushed a button, you can sort of see there that there are some pulses coming out. Well, some students were like, how does this code convey information? Some of them thought of, you know, Morse code, of how you have the dots and dashes, or like in the cameras, there's that binary on and off with the light. Well, we decided that we wanted to measure some of these signals to see if we could actually figure out what was going on. So to do that, we got this Arduino set up. It has an infrared sensor on there, there's a breadboard, and essentially you can shine the remote and direct that signal towards the sensor. And the data that you'll get from the program will look something similar like this bottom graphic there, where there's some ones, zeros, there's some very discrete waveforms there. And so these pits that we're seeing are really similar to what we saw with the CDs and the camera sensors, right? Those little pieces of information, those little pits. So that's pretty cool. So then students start thinking, okay, well, light or these EM waves can carry information. There is a code, and it turns out that each code or structure, it correlates to a very specific function. So here we're sort of seeing it in another way where the structure of the actual waveform will correspond to a very specific function that we're asking the device to do. And later on in this unit, in this bend, we'll explore other parts of the spectrum also, in terms of radio waves, X-ray. Are we going to see very similar signals? And it turns out we do. So some of the takeaways from our final bend here includes just being able to model how these waves are transmitted, how these digital signals are a little bit more reliable just because there's less variations in amplitude and frequency, right? We're looking at these discrete pits versus those continuous sort of waveforms. An example of this actually is maybe if you're playing your favorite car radio station and it works for a certain radius before it gets staticky. So we're comparing that signal to, say, a satellite radio where we can get a lot more distance for uninterrupted listening. In this bend, students will also have a better understanding of how these waves interact with matter. A lot of our students are really interested in just the applications of these waves too, and they'll bring in ideas such as, radiation therapy, MRIs, GPS. And so we want to start investigating some of those pieces too. And so an option is to have a capstone project for the students in this unit where they can explore those other applications and tie in, well, what does the structure of those waves look like, and how does that affect the function of whatever technology they're looking at? How is that information sort of encoded into the device itself? So just bringing it back to that original anchoring phenomenon, students can better answer why, let's say you have better signal in one part of the building versus another, or why does your call get dropped? So all these pieces is what we're trying to address here in this final bend. Before we conclude our presentation, let's just take one last moment to reflect back on these past few moments. What questions do you now have? And maybe you want to start thinking about what pieces you might be interested in taking away into your own classroom as well. All right, so going forward, like we said, this is just a draft of a curriculum. We haven't trialed this entire updated unit yet. We've only piloted certain sections of it. So we do plan to trial this updated unit in its entirety in a high school physics class coming up, adjusting, of course, to remote or hybrid learning as needed. In addition to that, we'd love to get some feedback from you, students, other colleagues for our curriculum design. So this QR code here on the right, it links to just a brief survey on just some of your takeaways from our presentation. You could also type in this bit.ly link that's down below as well to access that survey. The curriculum, though, is something that we would love to get some feedback on. So it is linked in the survey, and we'll also have a link to it on our next and final slide as well.
So thank you, Sunny. Thank you to you all for listening. Hopefully you got some new ideas from this. And as she stated, we'd really love if you had some interest and would take a chance to look at a little bit more depth at our curriculum. Give us some feedback. And there are some other units out there that do similar things, but we really try to make this a unit that hits all 5 performance expectations in depth, and then also includes some of the other things about waves, like the Doppler effect that you would usually want to cover in a high school physics class. So please check out the curriculum, check out the survey. If you are interested in trying portions of this, obviously what we have is pretty rough still, but we'd be happy to chat with you. Our emails are there. And also I just want to thank Eric Garay, who I worked with on the very initial 3-lesson iteration of what has now become a 26-lesson unit. And also Michael Novak at Northwestern, who has supported us with design help at various parts of this process. Thank you all and take care.
Thank you.